Everyone, I'm Bolin Li. Welcome to my XC paper presentation. My paper topic is OJXPerf, Featherlight Object Replica Detection for Java Programs. Now, the Java programming languages has been around for more than 25 years. Still is regularly among the top 2 programming languages used in the whole world. Java can be used to build applications for a wide range of platforms, desktops, servers, mobile phones, templates, televisions, and web browsers can all use Java. And the developers want their Java-based applications to run faster and consume less energy. So the Java performance concerns are everywhere. Currently, in Java profiling, the classical profiling techniques usually target hotspot, that is high resource utilization, such as high CPU usage, cache misses, access latency, memory allocations, and some other hotspot metrics. Hotspot analysis is indispensable, but it cannot tell whether the resources are well spent. We also investigate some of the state-of-art Java inefficiency analysis tools. Most of them bring significant overhead because of no support with hardware sampling, and very less of them can provide cross-object analysis. Even some tools focus on object-level inefficiency. None of them can detect redundant computation caused by object replica. The performance issue detected by OJXPerf is object replica. Here is the definition of object replica. We have two objects O1 and O2. They have the same allocation context, which means they are allocated in the same place of the source code. If every field of two objects are identical, then O1 is a replica of O2. You may wonder how series of object replica occur in Java applications. With the help of OJXPerf, this figure quantifies the ratio of object replica over the total number of objects in several real applications and two popular Java benchmark suites, Da Capo and Renaissance, showing that replicated objects are pervasive in modern Java software packages. So it's worth to investigate such inefficiency and optimize code to avoid object replica. So why object replica appears? Here I give an example on image processing. We investigate a Java application that divides a graph into small size blocks, like this fish picture. To process the image, the Java application creates an object for each small size block instead of creating a single object for the whole graph. Consequently, some of the created objects have the same content due to the good value locality among all adjacent blocks. In this picture, we can see some adjacent blocks have the same color. In our paper, we propose OJXPerf, which is an efficient object replica detection for Java. Like I said, Java languages is one of the most widely used languages in production, but Java language also has its own challenges for profiling. It depends on the management of JVM to allocate and reclaim memory instead of programmers, which improves the security of applications and lightens the program's burden. But on the downside, as a developer, unaware of underlying memory accesses is a performance handicap. Also, the JVM brings challenges for profiling, that is JVM abstraction. The JVM is a virtual machine that runs Java class files in a portable way. Being a virtual machine means the JVM is an abstraction of an underlying actual machine, regardless of what operating system or hardware is actually present. The JVM creates a predictable environment for a program to run within. Here are the design principles of OJXPerf. First, to focus on problematic object issues, we develop a object-centric value-aware profiling technique, which provides rich information to guide optimizing object replicas in JVM-based programs. Second, OJXPerf can be directly deployed in the production environment. That means OJXPerf doesn't modify the application source code, the JVM, and the operating system. OJXPerf is running on common CPU processors. The third one is lightweight. We want OJXPerf brings as low as possible overhead. To achieve this, we use sampling technique and minimize the bytecode instrumentation. To detect the object replica, what OJXPerf needs in Java. Here I list three abilities: the ability to instrument object allocation, the ability to monitor hardware events and CPU execution, and the ability to break the JVM abstraction. Let me talk each of them. First, how to enable OJXPerf to instrument object allocation. We use ASM framework to do it. So ASM is a framework that allows manipulating and generating JVM bytecode. So ASM provides APIs to traverse Java classes, so we can instrument object allocation by hooking the object allocation keywords, which includes a new array, and a multi-new array. Then OJXPerf can capture the object information, such as its allocation size. Next is about how to monitor various hardware events and the CPU execution. To monitor hardware events, we use the hardware performance sampling units, the PMU. PMU can be used to count various hardware events such as memory loads, stores, CPU cycles, cache miss or heat. Registers can be configured in sampling mode. When a threshold number of hardware events elapsed, PMU triggers an overflow interrupt. Intel offers precise event-based sampling, the PEBS, in Sandy Bridge and the following generations. PEBS provides the effective address at the time of sample. To monitor CPU execution, OJXPerf uses hardware debug register to trap the CPU execution for debugging when the program counter PC reaches an address breakpoint or an instruction access a designated address, the watch point. Finally, how to enable OJXPerf to break JVM abstraction. We take advantage of Java Virtual Machine 2 interface, the JMTI. So JMTI is a native program interface of JVM. JMTI provides a number of event callbacks for example, capture JVM start and end, thread creation and destruction, method loading and unloading. User-defined functions are subscribed to these callbacks and invoked when the associated events happen. Also, JMTI maintains a variety of JVM internal states, such as the map from the machine code of each JIT method to bytecode and source code, and the call path for any given point during the execution. So tools based on JMTI can query these states at any time. By now we know how the OJXPerf instrument object allocation, monitor hardware events, trap CPU execution, and break the JVM abstraction. In OJXPerf, to monitor consecutive memory access, we combine hardware performance monitoring units and the debug register available in the CPU processors. We use PMU to sample memory access. That's the first access to a memory location. Hardware debug register can trap program execution when a designated address is touched. We use debug register to intercept the next access to the sampled memory location. Let me give an example to show how we combine PMU and debug register. This is a memory access sequence in the timeline during program execution. The PMU takes a sample when the program is touching memory location M1. In the meanwhile, the debug register sets a watch point at M1 to monitor the next memory touched from M1. Then the program continues as normal until the next touch from location M1, which triggers a debug register trap. Next, I'm going to give the details about how debug register works in object replica detection. So like I mentioned before, OJXPerf leverages debug register to set up watch point, which traps the program execution when the designated memory are accessed. Here, assume we have two objects, O1 and O2. O1 and O2 are two distinct objects that have the same allocation contact, and O1 is created before O2. So here O1 and O2 form an object comparison pair. OJXPerf uses queues Q1 and Q2 to store PMU symbols taken from objects O1 and O2 respectively. Let me introduce the process in objects O1 first, because O1 is created before O2. For O1, we simply collect its PMU samples. So this figure shows the workflow in objects O1. When a symbol taken from objects O1, OJXPerf uses a tuple, OFF, the offset, and V, the value, to represent it, and adds this tuple to Q1. So in this figure, on the left dashed square, we have the first tuple. So this is the first PMU symbol taken from object O1. Here, the offset 1 is the offset between the PMU symbol address and the starting address of object O1. And V1 is the value stored at the simple memory address. So in this figure, we can see when the first PMU symbol is taken for O1, we store the offset 1 and V1 information as a tuple, and save this tuple to Q1. For the nth PMU symbol, we do the same thing, put the tuple offset n and Vn to Q1. Next is about the process in object O2. When a symbol taken from O2, OJXPerf not only adds a tuple offset and V to Q2, but also retrieves a symbol from Q1. So this figure shows the objects O2's process in two different timelines, T1 and T2. At time T1, a PMU symbol is taken at offset M and save this offset M and with its value to Q2. In the same time, we also retrieve a symbol from Q1. The retrieved information in this tuple is offset n and Vn. Next, we use a debug register to set up a watch point at offset n. At time T2, the watch point at offset n is triggered, and we find the value at offset n is Vn prime. Then we compare the values Vn and Vn prime at the same offset of objects O1 and O2. We might have more comparisons between O1 and O2. In our paper, we have studied more than 50 applications, and based on our experience, if more than 60% of such comparisons report identical values among our detection pairs, we claim that the objects O1 and O2 suffer from object replica. We have the theoretical proof in our paper to guarantee the analysis accuracy of OJXPerf's sampling technique. Here is the overview of OJXPerf's profiling. OJXPerf consists of two components, object-centric analysis and duplication detection. These two components are implemented within two agents, a Java agent and a GMTI agent. The Java agent adds lightweight bytecode instrumentation to capture object allocation information during execution, such as the allocation contact and the address range of objects showed in this figure. The GMTI agent subscribes to Java thread creation callbacks to enable PMU to simple memory accesses. When the PMU interrupts a thread with a sampled address, OJXPerf associates the address seen in the sample with the Java objects enclosing that address. So this process is called object attribution. Moreover, to identify the object replicas, the GMTI agent programs debug registers to subscribe to watch point. So next, several slides are gonna show the evaluation results of OJXPerf. First is the overhead analysis of OJXPerf. The runtime overhead is the ratio of runtime under monitoring with OJXPerf to the runtime of the corresponding native execution. Same for the memory overhead. To quantify the overhead of OJXPerf in both time and memory, we apply OJXPerf to three well-known Java benchmark suites: Renaissance, DaCouple, and SpecJVM 2008. We run every benchmark 30 times and compute the average and error bar. From the last column of these two figures, we can see that OJXPerf typically incurs 9% runtime and 6% memory overhead. Here I use an application named Suit as a case study to show how to detect and optimize object replica issue. So Suit is a framework for analyzing and transforming Java applications to bytecode. So this figure shows the snapshot of OJXPerf's flame graphs GUI in VS Code. The top pane of the GUI shows the Java source code, and the bottom shows the flame graphs of objects accesses in their full call stacks. In the flame graphs, the x-axis shows the accesses with their call stacks to object replica, and the y-axis shows the call stack depth, counting from 0 at the top. Each rectangle represents a stack frame. The longer of the width of rectangle, the more identical comparison for this object. The GUI in this figure shows one problematic object, ST highlighted in blue, which is allocated on line 83 and accessed below its allocation. By investigating the source code, we found that the contents of object ST keeps unchanged during the execution, but this part of code is repeatedly for hundreds of times. Since the contents of object ST is unchanged, we don't need to have this while loop to iterate every element inside object ST every time when this part of code is invoked. This optimization has 1.17 times speed up to the entire program. By using OJXPerf, our optimization patches for several cases are confirmed and upstreamed, for example, the application suit and fun bugs. As I cannot talk about all the case studies I run in the paper, so I just gave a table that overviews the performance improvements on several real-world Java applications guided by OJXPerf. For each Java application, we pinpoint the problematic code location. Under the optimization columns, we provide 4 measurements. They are whole program speedup, heap usage reduction, L1 cache misses reduction, and executed instruction reduction. And finally, I would like to give the conclusion of this paper. We developed a novel object-centric value-aware profiling technique in OJXPerf. To reduce measurement overhead, OJXPerf employs the PMU in conjunction with hardware debug register and minimal bytecode instrumentation, which typically incurs 9% runtime and 6% memory overhead. Also, we quantify the theoretical lower and upper bounds of analysis. You can read our paper for further details on this. For easy use of OJXPerf, OJXPerf is applied to unmodified applications, JVM, and operating system. And lastly, guided by OJXPerf, we are able to obtain significant speed ups by eliminating object replicas in various Java programs. All right, that's all my presentation. Thank you.